All right. Progress on to the next one. Okay. So deep autonomy is the next discussion. I'll set up a couple slides here and then hand it to Ram and Katie. What I talked to you about in the last 45 minutes was this safety use case. Going forward on deep autonomy, the real motivation here is improved profitability. So creating a business-oriented use case. And the idea is within the constrained, world of a depot, how could we take vehicles that have ADAS sensors on them, add support from infrastructure sensors, and have that allow us to marshal the vehicles through the depot, or the drones in the future through the depot, in autonomous ways. And what we'll go through in the presentation, I'll talk just very briefly on systems engineering because we're just ramping that up. And then Katie and Ram will take you through the virtual environment that we've built of the depot, as well as the perception work that they're doing and the planning work as well. Just to refresh everybody's memory on the use case, the idea is, today when, an Amazon Prime delivery van comes in here empty, they got to drive it to the warehouse, park it here, get it loaded with packages, wash it, charge it, do some checks. So there's a bunch of sort of downtime for the driver as he's just marshaling his vehicle through this depot. And the idea is, could we do all the marshaling autonomously and let this driver just come in, drop off this empty van, go jump in a loaded van and go back out and start delivering packages, right? Because that's when he's doing the real value-added work for the company. And then could we do this part behind the fence, could we do that autonomously, where, the infrastructure would take over and say, okay, this vehicle, I want it to go to this spot in the warehouse first. So that's what we're going to create. The first year of this project is going to be completely virtual, because obviously building a brick and mortar depot is expensive, and we want to make sure that we make all of our mistakes and learning, in the first year when we're in the virtual environment, moving pixels around rather than brick and mortar. So safety engineering, real quickly, Gaurav Pandey, who's an associate professor at Texas A&M, is going to lead this work. Gaurav and I actually worked together at Ford, so that's was the connection. But Gaurav has a lot of great experience, and he's going to be leveraging two folks from Henry's MTL lab, Ting-Han Wang, who is a postdoc, and Gigi Chow, who is a PhD student at this point. So Gaurav will be leading the work and guiding Ting-Han, and Gigi will be doing most of the work. And we'll go after the typical questions, like what are the functional requirements, and how should we architect the system to meet it? Safety of the intended function. So how do we ensure that our system's intended function is acceptably safe, even in the presence of the unpredictability that you get in real world scenarios? And then functional safety, which is, in the event of hardware and software malfunctions, how do we make sure that our system is still robust and minimize the effect of any hazards? And here's all the work we will do. I'm not going to take you through this in detail. But, the systems engineering tasks are down here. The safety engineering tasks are up here. We're going to focus more of our work on the concept level. So giving you documents in the end that would say, at the concept level, here's how you would make one of these. We are going to do the implementation level, but those documents will be less reusable for you because that would depend on what your depot looks like, what kind of vehicles you have, where your cameras are located. So once you get into implementation, everything gets more specific, which is why we're going to focus more of our work on the concept level, where we will say, in order to do this depot autonomy use case, what are the requirements that it has to meet to do that successfully? And what hazards would that create? What are the risks? How do we mitigate those risks? And then how do we architect the system? And how does that come together into creating a functionally safe concept with a set of requirements for how to implement depot autonomy? So that'll be the main thing that the team is working on. And then here's where I'm going to hand off to Katie and Ram, and they can take the rest of the presentation from here.
Great. Did you share the screen?
Yeah.
One second. We're just sharing our screen here. So.
Oh, okay.
I think it was screen one there.
Oh, you want me to stop sharing here?
Yeah, I think.
Okay.
I think that'll be easiest.
All right.
Or it's that one. Great. So hopefully everyone can see our slides.
Oh, hold on one sec.
Oh, okay.
Unless they just seamlessly switched over. Maybe you guys are so good I didn't even see the flicker in the matrix.
Working.
All right, go ahead one slide and let me make sure. Yeah, I see your mouse, so okay.
Okay. Excellent. So I'm Ram Vasudevan, and this is Katie Skinner. So we're both faculty members in robotics, and so we're going to be talking a little bit about developing this depot autonomy project that Greg just introduced. On this team, we have Sean Rice and a few GSRA, so graduate students who are working on this, Seth, Shallon, and Frank. So again, I think the core idea here is that we wanted to try our best to leverage what we had available in our prior research. And in fact, sort of the core questions we're interested in answering is how do we leverage infrastructure-mounted sensors along with lower-cost moving sensors to do mapping and scene understanding. And the way that we're going to do that is by developing a really nice representation of the scene and then use that scene representation in order to do planning and control. So this high level is a description of the questions we're interested in answering. Before I do that, I thought I would talk just a little bit about the way that we're thinking about this problem and why we're interested in this and the way that we're coming to attack this. To try to contextualize this, it's worth taking a moment and just thinking about how people think about autonomy at the moment, and it really appears in a spectrum. So on one end of the spectrum is, sort of the way that most AV companies think about this problem, which is they have dozens of subcomponents. So that is things like modules that are doing things like localization, mapping, object detection, tracking, planning, control, etc. There's a bunch of these different modules, and what they do is basically take these different modules, develop them within local engineering teams, and then try to stick them together in a way that can realize full-scale autonomy. And in fact, this has been the approach that almost every AV company has taken. So it could be Waymo, it could be Cruise, it could be Aurora, it could be Latitude. Many companies have thought about basically this approach. And the idea here is that each of these subcomponents is really well understood. And you have a group of engineers who have a lot of PhD training working on this problem. They develop an algorithm, and then the goal has to be fitting it together with these other algorithms that are developed by other teams. This is really great, but it's pretty expensive. And the amount of code and engineering that has to be done can be fairly unruly, which has made a lot of startups and others think about a different approach to this problem, which I'll call sort of the pixels to torques approach. The idea here is that I just have, all of my sensors. I apply some fancy learning algorithm that basically takes all that sensor input and then translates it into the torques that I apply into my self-driving car. So notably, companies like Tesla, for instance, or even, companies like OpenAI have been very excited about this approach because basically it removes all of the complicated engineering that has to be done by these other approaches and builds just a single module that essentially is deep learned directly from data. It's really compelling in that it simplifies some of the engineering process and it mimics our understanding of how human beings or other biological systems work. On the other hand, the challenge is it's basically a black box that we don't really understand the ins or outs of. So you're, transforming throwing away all of this modularity, but you're sacrificing all of the safety. And what this project is really focused on is maybe something in the middle, and that is basically just taking exclusively a two-module approach. And in the first module, we're building a representation of a scene, and we're going to do that by using a deep learning approach that is really well understood. And the second module is going to apply motion planning and control. Again, a module that is really well understood where we can make really nice guarantees about the correctness of these algorithms. And so I'm going to, Katie and I are going to spend the rest of the presentation talking about this. I think probably many of you have thought about, planning and control. You've probably operated a cruise control system, so you understand sort of how that kind of control works. But the module number one, which is the scene representation, may be something that you're not aware of. So I'm going to spend a few slides here just talking about that at a high level. And so the idea here is, I have an implicit representation. That's what we're going to try to construct. And, I'm going to try to give a small example to sort of walk through what this representation is actually doing. So here I have a drum kit. And let's say that I wanted to understand what this drum kit was and build a representation of it. And what do I mean by that? Well, what I want to understand is, what does this drum kit look like when I look at it from another perspective, like another view from the, separate from the one I'm looking at here. This is a thing that all of us as human beings are able to do reasonably well. So, you can close your eyes and imagine for a moment, what does this drum kit look like from a different view? And you probably have a really good idea of it. As it turns out, that idea is what is actually allowing you to do quite a bit of planning and control, because you know what this drum kit's limits are, what its size is, what it looks like from different perspectives, what it's going to behave like if you try and hit it. Well, what we want to be able to do is to build a representation that can do this. So the core idea here is that what we're going to do is assume that we have access to a sequence of sensor measurements. So what does that look like? So in this instance, we have this drum kit. And in fact, we get a lot of different images of what this drum kit looks like. And so you can see the locations from where we get these different images. And our goal is to build an output, which is basically going to correspond to the probability that a portion of the scene is occupied from a particular perspective. So what is that going to allow us to do? In fact, what it's going to allow us to do is figure out or predict what the scene would look like from different perspectives, kind of like, our imagination was just able to do. And in fact, that's going to be the core of what module one is actually going to try to construct, which is getting scene measurements from sensors. Those could be LiDAR, it could be camera, and then translate that into a single representation, which you can then query to understand what the scene looks like from different perspectives. In fact, we've actually already done some of this work. So our prior work has actually shown how to build these implicit representations for static scenes. So on the right-hand side, you're seeing a depth image. Blue means you're very close, and red means you're far away. And in fact, you can see what the scene looks like, a real scene looks like, on the top right. On the left-hand side, you're actually seeing the trajectory of the robot as it's moving through the scene. And in fact, you're seeing not only that we're constructing a depth representation, but in fact, we're also constructing a mesh of what this world actually looks like. And this is actually the trajectory that the robot took when it constructed this scene. But in fact, we can actually show you what the scene looks like from novel perspectives. These are poses of the robot that it had never seen before. But in fact, we can still tell you what the world would look like from that perspective using this implicit representation. And this representation, which we call loaner, was actually constructed by using a LiDAR. It was actually constructed in real time, but in fact, our prior work has also shown how we can construct this using RGB and LiDAR. And in fact, I can show you an image of what this looks like. Maybe we'll click ahead here. And in fact, this is what it looks like on a real world scene outdoors. Again, in this instance, we're fusing together both LiDAR information and RGB information. And in fact, this is the kind of thing that we want to be able to try to do now inside of our warehouse in simulation to start off with. And now in this instance, we're not going to have the LiDAR and the camera sitting on top of each other. We're going to have them, mounted separately from one another. And in fact, that's what the remainder of this presentation is going to be about. We're going to start off by talking about this warehouse simulator. Katie's then going to talk a little bit about implicit representations. I'll talk about motion planning, and then we'll discuss what we plan to do next. Katie?
So I'm going to tell you a little bit about the warehouse simulator that we've been developing so far. So as Greg mentioned, the first year of this project will be tested and developed in simulation so that we can work out all the details before we move to the real world. So the goals of developing the simulator are to enable us to generate simulated sensor data of the environment and develop new methods for safe navigation throughout the environment. We have started using tools like Unity, ROS, and ARVIS to get a jump start on the simulator development. And we're thinking now about moving over to Carla as that Carla MCity model is being developed, as Greg mentioned earlier. But in this simulation environment, we can generate sensor data from many different sensors of our choice. So we can generate LiDAR data, RGBD data, IMU, and GNSS data if we choose. So here's kind of a fly through of the simulated environment, so you can maybe recognize some of the roundabouts in MCity. We've selected a location off of the MCity streets, which could be a potential location for the real warehouse. And you can see in the outside of the warehouse, we can add different features such as refueling or recharging stations. We can add wash stations. There's really a lot of flexibility in what we can add here. And again, so this is all developed in Unity by our research engineer on our team, Sean Rice. And our next steps are looking to move this over to Carla, but we expect to have the same flexibility for the types of structures that we can add. And moving to Carla will allow us to use that MCity model that is being developed currently. So we can see as we fly around, we can really visualize the full warehouse, and we'll go inside in a second. So then inside the warehouse, again, we have flexibility how we would want to set this up. So when we have the real warehouse in the future, we can actually design the simulator to be a perfect model of the real warehouse so that we can have kind of a one-to-one representation here. But you can see in the simulated warehouse, again, we can add indoor features of interest as well. So just some of those features closer up, again, we could have something like a recharging station, a loading dock environment. It's really up to what we want to add to mimic the real world environment that we expect to see. And then indoors, we can add other features as well. So we can add not just static storage shelves or static features, but we can also add things like robots that are moving around and interacting with the warehouse environment. We can add other infrastructure that is dynamic so that we can really model all the complex interactions that happen inside of this warehouse. So having this simulated environment is really powerful. It's a great resource to have because it allows us, it gives us an environment where we can go through and collect data in any trajectory from multiple modalities. So here's an example of a data collection trajectory that we're able to carry out. And we can see that we can collect different types of simulated data when carrying out this simulated trajectory. So here's an example of LiDAR data. For this project, we are focusing on LiDAR data that might be mounted to the fixed infrastructure. So if we want to see a dynamic scene where we might have some moving objects moving throughout the scene, since this LiDAR is mounted on fixed infrastructure, it will remain static aside from tracking those dynamic objects. And again, this is all simulated data that we're able to collect through that data trajectory. And a couple of things to note here are, again, we have flexibility on where we want to put the LiDAR. We have flexibility in how many infrastructure sensors we want to include. So one aim of this project will be evaluating kind of what the most effective configuration is for that infrastructure LiDAR for the warehouse problem. We can also generate simulated data from moving vehicles. So we're focused on low cost sensors from moving vehicles such as RGB cameras or RGBD. So here's an example of a simulated rendered RGB image on the left and the simulated depth image on the right. So for the first stage of this project, we'll be focused on that infrastructure LiDAR and the simulated data from the moving vehicle. So what we've done now that we have this preliminary simulated environment is we have tried to leverage the work that we have done in implicit representations for LiDAR and RGB data to input this simulated data and see if we can learn an implicit representation of our simulated warehouse environment. So this video shows the rendered images from novel or from viewpoints when we are moving through that implicit representation of the environment. So you might think, this looks a lot like that simulated data. Well, that's great. We're getting really high quality implicit representations that we can then move to any viewpoint and render novel viewpoints for RGB, novel viewpoints for that depth image from the moving vehicle. So this is all this is all viewpoints that are queried from our implicit representation, which means now we have a really good internal understanding of the scene that we can then leverage for planning in the next module. So Ram's going to talk about the work in planning.
Yeah, so we've just gotten started with basically the first portion of this project, which was that implicit representation. So now I'm going to talk a little bit about work that we anticipate doing, and the way that I'm going to talk about that is by first talking about so the problem that we're trying to solve and the algorithms we've developed in the past that we hope to apply as this year proceeds forward. So to contextualize the planning and control problem, let's go back to sort of the autonomous vehicle case. I think Greg has been talking a lot about roundabouts, but maybe I'll talk about a slightly different problem. So here we have a left turn. So here's my ego vehicle. And, I have a waypoint. This is potentially the place that this black car wants to actually get to. And, what we have now are things in the environment. So these could be dynamic vehicles or dynamic pedestrians. And in fact, when I apply a traditional approach to modeling these kinds of things, what I end up getting is a probability distribution that describes the locations of these objects, right? So we don't know perfectly where these things are. And in fact, the module that we've developed, this implicit representation module, is actually capable of giving us these probabilistic representations of static objects so far. But in this instance, let's imagine that we have a probabilistic representation of not only the static objects, but the dynamic objects in the scene. The goal in this instance is to try to find a trajectory that can avoid these probabilistically located objects and get to the waypoint or get to it as closely as possible. And so in this instance, generally that's solved by or represented by solving some sort of optimization problem. And in fact, that's what I'm going to talk about, a method that can actually do this while providing useful guarantees about correct operation. So great. So in fact, I have a lot of prior work in this area on doing probabilistic planning and control. This algorithm we've called Radius. It was something that we developed last year. The way that it works is in two pieces. There's something that's called reachability analysis, where we essentially construct these box-looking representations for what the dynamics of the vehicle will allow the vehicle to do. And then once we have those box representations that we construct offline, then what we try to do is to select from inside of those box representations a motion that we can certify will actually avoid running into these probabilistically represented objects. I'm going to talk a little bit about how each of these different modules actually works. So that'll be next. So the first step, this reachability analysis, what it does is it begins by parameterizing the control input of the vehicle. So this could correspond to different types of motions that the vehicle may take. So for example, this may be lane change maneuvers or maneuvers where I speed up, or maybe even maneuvers where I make a sharp right turn. These could correspond to left turn or right turn maneuvers, any type of maneuver that you may be interested in. What we do is we take these different kind of maneuvers and we build a reachable set representation for this system. What does that mean? This reachable set representation is a box that essentially contains the trajectories of the system when they follow these different parameters that are depicted on the left-hand side. What we have is a really nice parameterized representation that we can then use during runtime operation in order to actually ensure that we act safely. So let's click forward here. So now during real-time operation, I get, maybe some information about the locations of these objects from my implicit representation. It gives me a probabilistic representation for where these objects are. And what we do is basically, we get information about where we would like the vehicle to go to. So maybe it wants to go to that black X over there on the right-hand side. Well, in fact, what we do is then write down an optimization problem where we search over the parameter space in order to try to identify a motion that gets as close as possible to that black X, while ensuring that in probability, we actually don't collide with these objects with some, epsilon guarantee that is given to us by some user. And in fact, the thing that we have done in the past is actually shown that we can solve this optimization problem elegantly in real time. And we've shown this in the real world, but I'm going to show you a simulation next. And this is an example of what that simulation looks like. This is all running in real time, in fact, inside of a Carla simulation. And what we're doing now is basically making these lane change maneuvers and decisions. What you should know is that this is all planning in real time in a receding horizon way, meaning that it generates a trajectory of a certain length. And then as it proceeds forward inside of that trajectory, it makes a decision to select a new trajectory. This is a simulation, but in fact, we've actually gotten this working also on real systems and illustrated that they can work effectively. And now our goal over the next bit of this project, look forward to it for a second, is to actually illustrate that we can take this radius algorithm and combine it with this implicit representation that we've developed inside of the simulated warehouse. So that's going to be our short-term goal. In the medium term, we'll start working on trying to extend that implicit representation that we had built for static scenes to begin dealing with dynamic scenes, with the idea that longer term, we combine this together with the radius algorithm that we've just described. And then finally, we'll talk a little bit about how we can effectively just deploy the sensors inside of this warehouse in order to minimize the number of sensors you need while still providing you with effective coverage. So that's a really high, maybe fast description of what we're planning on working on. Happy to take any questions if you have any.
Questions in the room?
Don't have to now.
And by the way, Greg, if someone does have a question, we can't hear them, unfortunately.
Yeah,
so
no, Helen has a question. Yep.
I'll ask it again. Can you use this word to estimate how many sensors you need to cover a warehouse of given complexity, size, layout?
So the question is, can you use this to estimate, how many sensors and where you need to place them to get good coverage of a warehouse layout?
Yep. So once we have the full system working, that's exactly what we plan to do. So we want to use that system to evaluate how many sensors we need, and also what the best placement for those sensors is for if we have the case where we have expensive infrastructure sensors, but low cost sensors on the moving vehicles. Yeah, so the flexibility of the simulated system for this year really allows us to play around with that and make some concrete recommendations on both sensor type, sensor, and sensor configuration as well.
Okay, thanks. Maybe, Ram, can you go back to the slide that had that continuum from the sort of end-to-end approach versus the modular approach?
Sure.
The whole presentation in reverse. So I guess, this is one of the takeaways I'd like people to take from this presentation, right? Is that, a lot of the stuff that I've been talking about, like how we're using the data engine, is to create those sort of modular sets of AI models that are shown, there on the right of the slide. And that's the way most of robotics has been done through time. And that's the way, a lot of people have approached autonomy. Then, of course, because everybody likes to swing between extremes, right? There's the all-in approach, right? Which is the other extreme, where you just have photons coming into your camera at one end, and you have, turn the steering wheel and operate the pedals at the other end. And there's some potential advantages to that, because then you just sort of let the network optimize everything, right? But the disadvantage is all the stuff we've been talking about in AI safety, which is when the network is doing all that sort of optimization as a black box that you can't see, you can't query really, you can't read it. It's a set of optimization weights. Then when things start going wrong, it's sort of hard to know why, right? And so that's why we're going to launch on the AI safety project, which says, okay, given that we can't observe what's happening in that all-in approach, how do we put safety guardrails around it to make sure that it doesn't do things that are explicitly dangerous? And the thing I like about what Ram and Katie are doing is that, instead of sticking at the extremes, they're saying, is there a really good sort of middle ground where you can maybe sort of get the best of both worlds, where you maintain some of the modularity, where you have sort of a perception framework and a planning framework as your two sort of big modules. And so that's what I think is one of the really interesting things we'll see as this project progresses is, how those different approaches work and what the strengths and weaknesses are. Because I think that's part of our role as MCity is to investigate these things and then bring that back as information to folks like yourself who are doing this work internally within your companies. So I just wanted to make sure that context was clear from the presentation so that people understood sort of some of what's new and different about this approach. Henry has a question.
Norman, I have a quick question. I recently saw some of the papers related to utilizing vision-to-language model, and you're also understanding and then also utilizing the understanding of the theme, and then how planning as well. Do you see your work some of the foundational models, vision-to-language models, will be useful, or this is not exactly a question, but more like on a comment in terms of how really the large language model or foundational model is utilized for either for cognitive driving or for
So Henry's question is to get your thoughts on how we might use large language models to do some of this work. Especially the one example he gave is the vision to language models that are out there. I think where you put in an image and it gives you sort of out the metadata of what it sees in the image in a text caption kind of a thing. So did you have any thoughts, Ram and Katie, on leveraging language models?
We may have two different thoughts, but do you want to fire first? And then I can.
Sure. I mean, I think the foundation models and integrating large language models in robotics is relatively new. So we haven't worked too much on this, but the results that I've seen are really promising. And I think thinking about how we can integrate this in future systems would be really interesting.
Yeah, so I have sort of a nuanced take. So I think this is really interesting stuff. I think the large language model work has been really interesting because there's a lot of labeled annotated data, which is basically the corpus of the internet, right? Which has made a lot of this totally feasible in terms of there's billions and billions and billions of pages of data that essentially we have a dictionary that has annotated for us that has made essentially deploying a web crawler easy enough to use to basically go and collect all the data we need to be able to do large language modeling. I think applying it, that same insight to robotic systems is a little bit challenging from two perspectives. One is the space is a little bit bigger. So you not only have sort of the language component, but the vision component and the motion component, like of a large, high-dimensional, high degree of freedom robot moving around in the world. What I would say is I think in practice, there's a lot of utility to basically taking some of the planning and control stuff that we're talking about in Module 2 and embedding that inside of the learning process that is being used to train these kinds of models. So in fact, not this project, but I have several students who are working on incorporating this type of planning and control framework as a module inside of the larger VLM setup that basically allows you to identify the gradients that you need to construct in order to more effectively leverage the limited data that you have for these kinds of problems. So one of my former students was working on this kind of stuff, and now he's at Figure AI. So I don't know if you guys have been following their stuff. but I think they just got $675 million from OpenAI to basically deploy their humanoids and do interesting things. The work that he was doing was essentially on that probabilistic planning and control stuff. And in fact, I think this morning they have a really cool video of maybe not taking this algorithm that I have down here, but a variant of it, and basically using that in some way with some language and VLM style thing to improve the ability of this robot to respond to commands that a human being gives it. So it'll be something along the lines of, hey, can you pick up that cup and wash it? And then it knows that it's not every cup, but it's the cup that is sitting in front of it, picks it up, knows how to basically do planning and control using an algorithm that looks similar to module 2, and then actually cleans it and then puts it away. Again, long way to go, because basically I think those are really limited algorithms where they've basically curated the data using some version of behavior cloning or imitation learning. And I think more needs to be done to generalize the performance of these kinds of things beyond what, sort of those videos look like. That was a long answer, so I apologize for that.
Okay. Thanks, Ron. Thanks, Katie. That was a good answer. What was the name of the company you mentioned?
Figure. Figure.
Okay. Yeah, we'll definitely look that up. The one thing that came to mind for me was I think sometime last year I read an article about a company called Waze that created a model called Lingo, where as they had their drivers going out and doing data acquisition drives to make data sets, one of the channels that they were recording was an audio channel where the driver would explain his decision making. So he'd be driving and he'd say, oh, my lane is slowing down, so I want to get over into a faster lane, so I'm going to do a lane change now. So he sort of articulated in language terms, what was then going to actually happen. And they were using that to train a model so that the model in the future could explain to the driver what it was about to do. So the model could say, as you're driving, the model could be saying to you, oh, traffic is slowing down in this lane. The next lane to the left is free, so I'm going to do a lane change now, which I thought was kind of an interesting, take on it. And their model, the company's Wave, and the model they were talking about was called Lingo. But yeah, it just struck me as another sort of interesting integration of large language models.
Yeah, it's interesting just to add to that. I think the challenge with a lot of these LLMs has been multi-step reasoning style things. So it's impressive that they can do sort of a one-step style thing, but the test for general, like the capabilities of these things has generally been like asking them to read or reason through like a complex puzzle. And many of them, even the ones that are put out by like Google and whatnot, tend to really struggle with these complex multi-step style things. In these robotics applications, that tends to be the hardest part of some of these problems, which is like the multi-step reasoning aspect of it. And so it'll be interesting. I mean, there's lots of new architectures, lots of new ideas on trying to tackle these kinds of things. But anyway, yeah, very, very cool stuff. We'll see what happens.